This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. We're diving into a fascinating paper today that tackles the ambitious goal of replicating OpenAI's O1 model, a significant leap forward in AI reasoning. What immediately struck you about this research?
The sheer scale of the undertaking. O1's capabilities are impressive, and the paper doesn't shy away from the complexity involved in replicating its performance. It's not just about mimicking outputs, it's about understanding the underlying mechanisms.
Precisely. The paper frames the problem through the lens of reinforcement learning, focusing on four key pillars. Can you briefly outline those for our listeners?
Certainly. The roadmap hinges on policy initialization, reward design, search, and learning. Each component is crucial, and they interact in a complex, iterative way.
It sounds like a delicate balancing act. Let's start with policy initialization. What's the challenge here?
The challenge is to equip the model with human-like reasoning abilities from the outset. We can't just start with a blank slate and expect it to learn complex reasoning through reinforcement learning alone. It needs a strong foundation.
So pre-training on massive data sets is the first step.
Absolutely. Pre-training provides the model with a vast vocabulary, grammatical understanding, and a general knowledge base. But that's not enough. Instruction fine-tuning is essential to align the model's behavior with human expectations.
And then there's the injection of human reasoning behaviors. How is that achieved?
That's where things get interesting. The paper highlights behaviors like problem analysis, task decomposition, self-evaluation, and self-correction. These can be either learned through supervised fine-tuning or triggered by carefully crafted prompts.
So fascinating blend of learning and engineering. What are some of the key challenges in this phase?
Balancing sampling efficiency and diversity is critical. We want the model to explore effectively, but we also need it to converge on good solutions. Ensuring domain generalization of these reasoning behaviors is another major hurdle. We don't want a model that only reasons well in a specific domain.
Let's move on to reward design. This seems crucial for guiding both search and learning. What are the key considerations here?
The paper contrasts outcome rewards, which only consider the final result, with process rewards, which provide feedback on intermediate steps. Process rewards are generally preferred because they provide denser, more informative signals.
So how do you design these rewards?
There are several approaches. You can get rewards directly from the environment, if one exists, or you can simulate the environment. Alternatively, you can learn a reward model from preference data or expert demonstrations. Reward shaping is another technique to make sparse rewards denser and more informative.
And what are the challenges in reward design, particularly for something as complex as O1?
Distribution shift is a major concern. The reward model is trained on data from an earlier version of the policy, and it may not generalize well to later versions. Designing fine-grained rewards for language models is also tricky, as the granularity of actions, token level, step level, solution level, can significantly impact the design. Choosing appropriate data for complex tasks is another challenge.
The paper emphasizes the role of search in both training and inference. How does search fit into this framework?
Search is essential for efficiently exploring the vast solution space. During training, search generates high-quality training data. During inference, it allows the model to think more, generating better solutions with increased computation.
The paper categorizes search guidance into internal and external. What's the difference?
Internal guidance relies on the model's own internal state, such as model uncertainty or self-evaluation. External guidance comes from the environment, such as rewards or heuristic rules. Often, a combination of both is most effective.
And what about search strategies?
The paper distinguishes between tree search and sequential revisions. Tree search explores multiple solutions simultaneously, while sequential revisions iteratively refines a single solution. Again, a combination of both can be beneficial. Specific algorithms like Monte Carlo tree search, MCTS, and beam search are discussed.
What are some of the challenges related to search?
Inverse scaling is a significant problem. Scaling up search can sometimes lead to worse performance due to distribution shift in the reward model. Avoiding overthinking on simple tasks is another challenge. We need to find the right balance between exploration and exploitation. And finally, improving the efficiency of search is crucial as it can be computationally expensive.
Finally, let's discuss the learning component. Why is reinforcement learning so important here?
Reinforcement learning allows the model to learn from interaction with the environment rather than relying on expensive human annotated data. This opens up the possibility of achieving superhuman performance. The paper highlights policy gradient methods, reinforce, actor critic, PPO, DPO, and behavior cloning as potential learning algorithms.
How do these learning methods compare?
They differ in terms of gradient variance, memory costs, and data utilization. Reinforce has high variance, while PPO and DPO are more stable. Behavior cloning is the most memory efficient, but it has lower data utilization. The paper suggests that a combination of these methods might be optimal.
What are the key challenges in the learning phase?
Improving training efficiency is a major challenge, as the search process can be computationally expensive. Learning a strong question generator to keep the model challenged is another area that needs further research. And finally, mitigating distribution shift in off-policy learning is crucial for stable and effective training.
The paper also reviews several open source projects attempting to reproduce O1. What are some of the key takeaways from these efforts?
These projects offer different approaches to the problem, highlighting the various trade-offs involved. Some rely heavily on prompt engineering, while others use reinforcement learning with different search and learning algorithms. They demonstrate the complexity of the problem and the lack of a single best approach.
Looking ahead, what are some of the most promising future research directions?
Adapting O1 to general domains requires robust reward models that can generalize across diverse tasks. Incorporating multiple modalities, e.g. images, audio, presents another significant challenge, requiring careful alignment between different modalities and the model's reasoning process. Finally, learning and searching with a world model is crucial for enabling O1-like models to interact with and reason about the real world.
So, in essence, replicating O1 is a monumental task, requiring a deep understanding of reinforcement learning, search, and the intricacies of large language models. Your insights have been invaluable in clarifying the complexities involved.
The paper provides a valuable roadmap, but the challenges are substantial and require significant further research. It's a fascinating area, and I'm excited to see the progress in the coming years.
That was a great discussion. Thank you for your time.